All right, welcome everyone. This is another fun session with our friends from all around the country and all around the world with deep learning adventures. If you're joining us for the first time, you can find us on Meetup, on YouTube, on Twitter, on LinkedIn, everywhere. You just Google for deep learning adventures. Joined by my great friends and co-organizers Robert and David today, and great friends from all around the world and around the country. Good to see you all. Let me share my screen real quick for some notes. This is just the vibe we're playing, some music. Yeah, you can find us on Meetup. We've been going through a time series adventure last week and this week, so super excited about that. And this session is recorded as well as all our previous sessions. You can find them. I'll post a link on the chat as well. We have a bit.ly for DLA YouTube. That's our bit.ly here. So you see we had multiple what we call adventures here on attention transformers that Dimitri led, on TensorFlow deployment, on different topics in data science, machine learning, and deep learning. Some guest speakers we've had in the past, as well as more entry to intermediate level coding sessions and interesting projects. So yeah, today we're going to continue our session on time series, and we'll be using the material from Kaggle that was recently introduced. And just to give you some more context, I'll head back here. So last time, Robert and David covered linear regression, trend, seasonality, and time series as features. Today we're going to talk a little bit about hybrid models and forecasting and machine learning, as well as briefly touch upon the actual competition behind the exercises of this adventure. It proved a really interesting challenge for us, and yeah, we have some cool topics to discuss together. Yeah, I think that's it. Let's dive right in. I don't think there's so again, I have all the links for Slack and all that in the Meetup page, as well as for my YouTube channel. Cool. So just as a reminder, so we started tackling, let me zoom in a little bit, time series from basic components. So if you remember last week, David and Robert talked a little bit about how do we just forecast a time series simply by estimating the trend. So just a flat line, for example. Then we added more complex features to it. We added seasonality, periodic seasonality. We added cycles, which might not be on point, like don't have a specific periodicity to it, but they, to us with the human eye, they look like they have a repeating pattern, and some error that internally the time series itself offers. So this module talks a little about these components, as well as the idea of, let me zoom in a little bit more, of the original time series, our fitted model, which is shown here in blue, and then calculated the difference. So the original time series minus our fitted curve, you will get this, what is called the residuals, or the leftovers, or the error. So then the goal is, okay, how do we minimize these residuals? Like in every machine learning setup, how do we actually minimize this, or how do we find a model that basically minimizes these residuals? This is for that tunnel traffic series that was introduced last week. And one approach to do that is learning the components individually. So we have the original time series here, which could have multiple components to it. So could have trends, seasonality, cycles, and so forth. So the first step would be to create a simple model to learn this trend and subtract the trend from the original series. That will give us what is called the detrended series, which is shown here. So now we don't have an up or downward facing series if there was such a behavior in the original time series. But we have other phenomena going on, right? We have seasonality, we have cycles, and so forth. So then we fit another model on this residual number one, and to detect the seasonality of the time series. So we do that, we get other residual number two series. That one might have cycles in it. We fit a model, a third model, to this time series for specifically for taking cycles. and then we get left with this error. So the goal is to find the best algorithm or the best approach or the best feature engineering for each model. And if you do this approach, hopefully at each time step, the residuals are getting smaller and smaller. And yeah, and then if you combine the outputs of all of them, hopefully you have a really good forecasting. So just how does that look in code? We have our training data. We're actually going to split them into, this is a two-step process, and that's why it's called hybrid. We're going to split it into two sets of features, what is called X-train1 here and X-train2. And they usually are different. They shouldn't be the same. So X-train1 maybe is a very simple time-based, date-based, or time-based features like we've seen in the past for training seasonality and cycles. And then we built a simple model to detect those time-based features. Then the second pair of features could be something else, maybe some kind of interactions that we have among our features, or maybe holidays, or maybe other events that impact our time series. So just like traffic, maybe, yeah, holidays, maybe some economic data, maybe weather, maybe whatever other features we can acquire. That would be the second set of features, X-train2. So then we use that as our input. And now we want to estimate not the original output, but the residuals of the output. So from our original target series, we want to subtract the predicted values from the first model. And we'll get another set of predictions. And then to get the overall prediction, we just need to sum them up. So this is this step here that we showed here, but going from here to here to here. It's not in 4 steps, it's in 3 steps. I hope that gives a little clarity. That's the general idea of hybrid models. I'll go over a specific example, but I want to make sure that this is clear. So if you have any questions, comments, feel free to put them in the chat or unmute yourself.
Nothing in the chat.
Okay, cool. So then let's look at a very specific example here. Oh, sorry, before I do that, something about extrapolation and the fact that different models have different extrapolation capabilities. So this topic talks a little bit about different models having this capability or not. So models like linear regression can extrapolate trends. So they can use the fitted data and they can produce a model that can hopefully extrapolate and forecast future values. But other models like random forest and decision trees, simply because they're doing all their statistics and fitting based on subsets of our data, they don't really have the capability of extrapolating to future values. And if you remember, we had this challenge as well with neural networks as well when we were doing time series prediction. And this is also sensitive to the different activation functions that you use. So if you want to do some kind of a regression, you probably need to use some kind of ReLU or linear activation function in the very end so that you're able to regress and actually produce values that are not bounded. But yeah, even in neural networks, you might have exposed your neural network to a specific range of values. And if you're trying to forecast many steps in the future, you'll see that the neural network won't be able to pick up that trend. Yeah, this model talks briefly a little bit about combining models or stacking them. Stacking them means that you use the output of one model as an input to a second model. So more like a serial, like a model-to-model chain. You're combining the output of one model as the input of the other. The other one would be maybe ensembling them or doing some kind of approach like we're doing here, where we're doing one model, calculating the residuals, and then fitting something of the residuals. Yeah, there's some links here for other competitions. and how they use different combinations of algorithms and models to do more accurate forecasting. I'm not going to go over them. Just a very basic example here of how do you do this hybrid approach on this retail sales. This is not the competition data, so this is completely different retail sales from the US Census data from 92 to 2019. Yep, US Census Bureau. So this is the original data set. I'm going to use a hybrid model to forecast it. So we have as our axis date, and then we have two targets we want to predict for 2 time series. This is multi-output basically. So we have sales for building materials in units and food and beverage in units. So first we're going to create our, sorry, let me start with this part here. I'll just highlight the important parts, right? So yeah, US retail CSV data. We'll use the months as well as the 2 indices. There are multiple indices in the original data set. We'll parse the month as date, and we'll index by that month feature. And we'll also set the columns instead of index. We're going to make them as columns. This reindex will make them as columns. We'll create a new data frame combining this, and this is what we're looking at here. And based on last week, if you remember, we wanted to detect seasonality trends and other periodic features. So we'll use this deterministic process. Everything is time-based. So everything is based on the index of y, the timestamps. We'll use a quadratic term here, and if there's any collinearity, if there's any multiple columns basically that are linear to each other, we're gonna make sure that we only keep one of them. Yeah, generate our in-sample data, and then we're going to keep the last four years, I think, yeah, for testing. We will fit a very basic linear regression model to this trained data set, and so that's the fitted one, and we will predict on the test set. So the test set, let's see how we generated it. That's from this trained test split, the last 4 years. Let's look at it in color. So it's the original data set in black, and then the trend the trend model, as you can see, is picking it up pretty well. So in blue is the one that was fitted on, and in red it's one on the test data that has never seen before. So it's trying to do a decent job. Obviously, you can see the trend is actually uptrending here, and our model is not able to. The trend-based model is not able to pick it up. That's for the food or for the building material time series, and for the food and beverage is a little bit more predictable, I would say. Cool. For the tree-based model, we need to convert our original time series from what is called the long format, where we have 1 time series per column. Sorry, from a wide format to a long format, where we have pivoting, basically, when we have our time series intertwined here as rows. That's a requirement for our second algorithm that we're going to use. So we do that, and we also want to encode the industries, right? Right now there are characters or strings. We want to label encode them, or maybe one hot encode them, so that our algorithms can actually use them. So yep, we do that here, and then we're also going to use, instead of month, I'm going to use that as a feature as well, the month of the date. So values between 1 and 12. Yep, and then so we're going to split it again, train and test split, and then we will create what is called this residual. That's the one that actually we are interested in. So this is the original time series. This is the one that we fitted before with a linear model. And this is the residual that we want to use, this tree boosted model. So we're going to fit our training data on this residual. And then when we predict, we will predict on the training data plus the fitted values from the linear model, as well as on the test data, whatever we predict with the second model plus whatever we predicted for the first model. So let's see how it looks now. So this is combining the two algorithms, right? So we have a better approximation of the original time series as well as forecasting. Still, we're not doing a great job here simply because the trend that was detected by the first model wasn't that accurate. But for the second one, food and beverage, looks like we're doing a better job here. Cool, that's the general idea of these hybrid models. And in the exercises, I'm not going to go through the exercises for the sake of time, but I just want to show you what other models you can use. And there's multiple links as well in the tutorial. Right, so the exercise mentions that you can use the open source version of Mars, the spline-based one. You can do linear or higher order piecewise approximations. So Mars is actually a trademark from the company that came up with the term. So the open source version of it is called Earth, and as well as like different regularized versions of the linear model. So L1, L2 regularization, and LR. R is between 1 and 2 for elastic net. That's for model 1. And then for model 2, you can use other tree-based approaches like these extra trees or random forests, or maybe k-neighbors, or even a simple neural network here from sklearn. So yeah, in this exercise, you build this class called boosted hybrid, and you can specify what model you're going to use for the first part, as well as what you're going to use for the second one to fit on the residuals. Cool. There's no comments or questions. I will go to the next module. So that was the hybrid models.
Sorry, is there time to ask you a couple of questions?
I'm sorry, say again.
Is there any time to ask questions right now?
Yeah, go for it, yeah.
Couple of ones I wanted to ask, like what metrics would you suggest we use to compare different model performances for, I guess, are we like treating them as like linear regressions and use the metrics for linear regression, or just specific to the hybrid models I'm asking?
Right. So metrics, if usually, so this is a regression task, right? So usually you'd use some kind of mean square error and different variations of it. There's root mean square. The one that we're going to quickly look at, the competition uses root mean logarithmic squared error. So yeah, some kind of a distance measure, right? For each data point, for each state, you want to see how far you are. So some kind of a metric, a distance-based metric. So I've usually seen squared ones. So you want to penalize, the higher this distance is, the more you want to penalize your model. You can use maybe like first order difference where large deviations get penalized the same as small deviations, but usually, yeah, IMSC is a good metric.
And then the other question I had was, what if we have gaps in our data? So let's say you have, I don't know, weekends. You get weekends where there is no sales, as an example, in the retail market. So I mean, I'm making that example up, but I'm working on a case where I got log information data for resource utilization of a system, and the system only works in the working hours. And then when it's not the working hours, then it's basically zero utilization for my resources. So that's kind of the challenge I'm having, or picking up the right window of, for aggregating. another challenge I'm facing. I don't know if they're relevant to this discussion,
Oh,
but I just
very, very relevant. Actually, the competition that we're gonna touch upon in the very end has 1800 time series, and many of them have this exact same problem. So we have data for some of them, let's say for a specific time period, and then they're all zeros, meaning we don't have any data. So we have data, we have no data. And that actually impacts your linear model. So if you're trying to detect a trend, that's what we're discussing with Robert and David over the week. If you imagine that for this part of my time series, I actually have no data or there's zero, my trend will be pulled down. So that will significantly impact my trend, which means that will impact my final predictions. One approach, if you can, maybe get rid of them, right? Like they're not offering any signal. There's no information in missing values. Other people may be able to extrapolate them. Like if you're here, missing data here, more or less you can extrapolate them maybe by a linear trend. I don't know what other approaches are there, Robert, David, or anybody else.
So specifically the idea of the fact that, you know, it's not open during business hours or weekends, not open on weekends. That is what I would call a seasonality, and you can actually capture that in your model with seasonality functions. So because that's a very regular seasonal, right? A season doesn't mean like a calendar season. It can be anything like that. So the weekend thing, I would think seasonality would be a good approach.
Yeah, one of the challenges of this data set was that not only did you have that, we also had lots of random stretches where the data were zeros, or just, you know, unexplainable drops really in the level. I don't know if, George, were you planning on going through the exercises and showing some of that?
Yeah, I will. Yeah.
Okay.
It's just an interesting discussion, and it will generate lots of questions. So I said it for the end of my session, keeping in mind that you also have your sessions. Right. Cool. Yeah. We'll see.
Thank you, guys.
Yeah. Cool. Just for brevity and for you know, keeping we have lots of content, so I'm going to move on to this last model with forecasting, and then we're going to switch gears. We're going to talk a little bit about the competition and some of the challenges with it. Then we're going to talk about something else with Robert and David. So this last session here talks a little bit about, it doesn't introduce new models or feature engineering or things like that. It actually talks a little bit about the nature of the problem, and specifically talks a little bit about when we have a forecasting task, how do we approach the problem? So what information do we have, right? What are our features? Do we have just the, like, for example, for the traffic one or the sales one, do we just have regular sales? We also have maybe holidays, or we can get that. In the competition, you're going to see we also have oil data, the price of oil in Ecuador. That's the country that we're going to look at. Apparently, Ecuador is very, the economy is very tightly correlated with the prices of oil. So I wanted to include that as well. Anything else like weather or any other indicators you might think might have some kind of signal to impact your target, you would include it here. And then so that's the target, the X's, and then the Y is what are we trying to predict? Are we trying to predict just one value, like single output? Are we trying to predict multiple values, multi-output? Are we trying to predict one value just for the next day, or one value at a time for the next 7 days, and so forth? So yeah, this topic talks a little bit about this, introduces some new terminology. So in blue here, we have our training data, and the last training data we have is called the forecast origin. That's the very last one we have. That introduces the concept of lead time, which basically says what is the gap between my training data and the first time I actually make a forecast. So in red here, we have the forecast. And then the forecast horizon is for how long do I want to forecast? 1 day, one data point, 2 days, 2 data points, 3 days, 3 data points, assuming these are days. Okay, if they're months, 1, 2, 3 months, and so forth, whatever the data type is. So you can have, as you can imagine, right, you can have different origins. You can look at 1 week of data, 1 month of data, or the entire training data. You might have small or no lead time at all. You might jump directly from training to prediction. That would be a lead time of 1. And then your forecast horizon could be as small or as large as you want, keeping in mind that the larger it is, the harder it would be for your model to predict. Cool. So just to expand on this a little bit more, I'm going to look at a very simple data set where this is just my example. So we're going to look at time series 0 to 19. I'm going to use different lag features. This is basically an autoregressive model. So we're going to use as features the values of the time series itself, but shifted by 2. So as you can see here, shifted by 2 won't have values in the beginning. Lag 3 won't have values for the first 3 rows, 4, 5, 6, and so forth. And then for the targets, we're going to use the original one as well as the forward ones. So basically, we want to predict 3 steps ahead using the last 5 values. We want to predict 3 steps ahead. That's the task. And then we have different strategies. How we're going to do this. So one approach would be end-to-end, like use your training data and you directly predict multiple outputs at once. In this case, 3 outputs in our example. So some models can do that out of the box, like linear regression neural networks. You can have the last layer here have as many nodes as you want, 1 per each data point. Tree-based ones, there's actually a workaway around it. They're going to look at soon, but by default they cannot do this. Another approach would be you build 1 model per each step that you want to predict. So I have 1 model that takes all my historical data and predicts just 1 step, day 1 in the future. I have another model, could be completely different, usually it is, that predicts just the day 2 value, and another model that predicts just the day 3. That's this direct strategy. And they're all independent models. The recursive one says, I'll use my existing training data, and then I'll predict the next time step. And then the next time step is actually now a feature for me, right? It's a known value. So I'll add that in my training data, and I'll predict the next time step. Now these 2 are in my training data. I'll use both of them to predict the third one, almost like a step-by-step approach. And this one only uses 1 model instead of 3, like the previous one. So predictions becomes features basically as we go over time, as we shift, almost like a moving average. We saw in the visualization that we saw last week, almost like a moving average. Now the last one is just a combination of direct and recursive. So we have 3 models. The first one just predicts the very next data point. The second one uses features from the output of the first model to predict just the second data point. The third one uses the output of the first 2 models to create the third data point. There's a simple example here, flu trends, that goes through, let's see, 2 different strategies. And you can see here we're using lags for our feature-based, as well as the multi-step targets for our Ys here. Actually, I have a better notebook to show you, which actually has the output of this. So let me find it. Yeah. I like looking at the actual. Yeah, this one. There you go. So, yep. I just wanted to look at the shape of the data series itself, 360 by 130. And it has different categories for flu variations. And we're just going to look at very specific ones. So the data set itself looks like this. So it actually, that was a neat, let me show you here. Yeah, maybe we did it somewhere else. No, that was for the multi-step. Yeah, so it's actually grouped by weeks, and there's different categories for different flu variations. Yeah, this is the one that I want to look at. This is where we actually set the index as weekly indexes instead of time-based or day-based. That was a nice feature in Pandas. We're only going to look at flu visits for now. There's multiple of them. And making the lags and the next steps gives us, so this is our axis. We're going to look at the flu visits for the last 4 days. We're going to predict the next 8 days. So that's a multi-output prediction. Cool. So let's see how this multi-output works. So that's our training data, and that's our, let me show you the code here. Yeah, linear regression by default will give us the multiple output that we're interested in. So that's our training data, that's our fitted data. And let's see, do we do some kind of, yeah. So we want to estimate how close, right? How close are our predictions. So we use this mean squared error metric on the training data and the fitted data, which is the predicted data using white X train as input, as well as on the test data, how we're doing on the test data. This is not really test data, this is like validation data because we have the value. So yeah, basically how we're doing on the training data and the validation data. And the lower this number, the better. We want to visualize this for each. So in black, we have the original time series. We have the seasonality here. And then for each data point, ideally, we should see 8. We should see 8 days of predictions. So using the historical information, we should be able to predict the next 8 days and the next 8 days and so forth. This is hard to read this graph for me, especially with the colors, but the point is that we use historical information. So 8 weeks, we're talking about weekly, that's our periodicity here. So we want to predict the following 8 weeks, which is 2 months. So what if we want to use maybe some kind of tree-based model that doesn't support multi-output? And this is where this module talks about this multi-output regressor from sklearn multi-output. And basically for us, it's just a wrapper. And that gives us the capability to run a model like XGB regressor, but that gives us the capability to not produce multiple outputs based on the size of X and Y. Yeah, and if you see here, it definitely overfitted on the training data. Its RMSE is very, very low. But on the test data, it did a little bit better than the linear model-based one. You might not be able to tell from the visualization, but from the code here, I think it was 530 something for the training. For the linear model, this is 526. And I wanted to show you a little bit more this.
George, just
yeah.
One observation I had, something that kind of disappoints me on this particular tutorial is the fact that, I mean, you correctly called it, it's not test data, it's validation data, because they actually have the values right already. Right. The other thing is when you're generating those lags, they're not generating based off the predictions, right? When they're doing the validation, you know, they're supposed to be doing it 8 days out. The lags go back 4 days, but at some point you're supposed to be generating those lags off of predicted values. They're not though. They're doing them off the real values.
Oh,
You see what I'm saying? And they don't show how to do that. And you would have to do that when you're doing actual work because you don't have the values to get the lags. You have to get your predictions as you go. And the lags have to be kind of like dynamically produced.
right. So
See what I'm saying? So there's like data leakage in here for that validation step, right? Because the features have some of the answer built in.
So I talking about this multi-step here where you create your Ys, right? When you create your Ys, you actually create
Not the multi-step, but when you generate the lags, right? For 4 days back.
right.
But if you're predicting day 6, you would have to use predicted values from 4 days back, right? But they don't do that. They're making it off of the actual values, the real answers when they're in their test set.
Yeah. I mean, if again, this is because it's training and validation, right? It should be treated as training and test, which means that you don't have the Ys. You have to predict
right.
them, then use them.
Well, you have some of them, but as you get further out, you don't. You have to use your predicted values.
Right.
Yeah, I had noticed that too. I think in this course they were sort of careful to not actually do that, and so they were only forecasting one time step out in many cases.
This one.
Oh, this one you can do multiple, right? I mean, you have 4 predicted values in the future, 4 weeks. The period this year is weeks.
Right, weeks instead of days. But same idea.
Yeah, same idea. Yeah. Cool. Quickly wanted to touch upon this multi-regressor. It made me look a little bit about multi-class and multi-output. So in scikit-learn, there's this nice breakdown of multi-class in one on the left and multi-output on the right. And multi-class, this is for classification specifically. We've seen this if you've taken the book machine learning, this is San Diego group is doing as well. We've seen this 1 versus 1, one versus less classifier. But that's one way of generalizing when you have a classifier that's a binary classifier. You're just predicting yes or no, or between 2 classes. What if you have 5 or 10 classes? Then you can extend it by building multiple models for one versus rest. So let's say I have 5 classes. I would be building one for the first model versus rest, one for the second model versus rest, one for the third model versus rest, one for the 5th, and so forth. The other one is where you have multiple labels. So basically my output is not just 0, 1, but it could be 0, 1, 2, 3, 4. This is what is mentioned by this cardinality here. And the output is how many of them do I have? Is it a single value or is it a vector? And I just wanted to show that distinction. This table, I think, is an interesting table. So you have multi-class classification. You only have one y, a single value. That could have, different cardinality. And then for multi-label, you have more than one. For multi-output as well, you also have more than one. And then depending if it's regression or classification, cardinality could be continuous or integer based. Yeah, this multi-output regressor, it fits one regressor per target, it's basically a wrapper that I don't know I was able to look in the backend on the code here of how do you actually predict, or how to use this wrapper, and it looks to me like you're looking at how many outputs you have. So let's say in our case we had 4 weeks. So you basically use the same model or estimator multiple times using your x's, but in a loop basically to create this multi-output feature.
It's the same model, but it's different instances of it, right? Because it's estimators there, right? It's a yeah. Okay.
Yeah, different estimators, yeah. Okay. Cool. the last thing I wanted to share with you is about this competition and some things that we tried, and then I'm gonna switch gears to something else. So this competition is very interesting. We spent quite some time on this. Just to give you an overview, we have store sales data from Favorita store located in Ecuador, and in terms of data files, we have a training CSV file, a test CSV file. We have some other extra stores or extra data as well, like stores, like that introduces state, city, or cluster, daily oil price, holidays, and some additional notes. But the training data itself, it's time series based. So we have date, we have store number, we have family, how many units of that family, how many items in that family were sold, and how many items were on sale that day. So I'm gonna switch here a little bit and talk about how we approach this. So yeah, we have about 3 million records, and the index is again store number, family, date, and sales and promotion. I tried different things here. So again, I'll clean this up, this notebook, and I'm gonna publish it so that you can take a look. But I tried different things. I tried looking at, so there are two ways to approach this. You can look at feature engineering or modeling, or both, right? So on feature side, I tried using a lot of historical data, a little bit of historical data, just last year, just last few months. On the feature side, I tried maybe label encoding the stores and the family IDs, one-hot encoding them. And on the modeling side, I tried different models. So without getting lost in the details, I'm just going to give you the overview of their performance. And what is critical is that in the notebooks and in the tutorials, you usually do forecasting on a one-time series. You take some kind of average and you do one-time series. But here the task is to do forecasting on close to 1800 time series. Cool. So the models that work the best for me is this trend seasonality based approach, and there's multiple ways to construct them. But after looking at some other notebooks on the competition as well, and looking at online a little bit, there's some fine tuning that needs to be done. But basically, these trend based ones were performing really good ones. I tried linear regression, a regularized version of linear regression as well, and fine tuning them, hyperparameter tuning them, and I'm going to show the results with you. Something to keep in mind when we're doing a linear regression from X to Y, we're actually doing 1800 parallel linear regressions, right? So we're treating the Y's here as independent time series. We're completely separating them. That store 1 automotive is completely different than store 2 automotive, and it's completely different than store 3 automotive. That might, as to us, that might seem like, okay, that maybe there's some information there that you can gain, but without me introducing other features, without introducing like cluster ID or store ID or things like that, just treating this as independent parallel predictions was a good starting point. And then I also want to calculate some kind of metric per family so that I can see how this works. I created my own methods here to basically keep track of all my experiments, and the things I'm interested in is I call this version, like what version this is, and what is the time frame that I'm looking for my experiment. So what is my minimum target feature or index for X, my maximum, same for Y, my shape, what model I used, what was the training, what was the MSLE, not the root mean square, but the mean square logarithmic error on the training data. And then also I want to submit this on the Kaggle competition here. Let me go back. So that you get a score when you submit it. And I also wanted to keep track of that. So you can You can see in the leaderboard here what's going on. So that was my setup. Let me go back. And then some plotting. I also didn't want to visualize some plotting as well. So just to give you an idea of how my experiments are structured. So we have a version, and I'll quickly touch upon what is the difference between different versions, what training set I used from when to when, similar for Y, what is my shape of my data, what model I used. This usually has any regularization steps as well. What is the training MSLE? This I fitted later after submitting, so this is not the latest. What is the family and what is the train MSLE for that family? This we only have available for the training set. This Kaggle MSLE is overall on the entire 1800 time series. Yeah, I tried different ones. Let me go to the actual visualization. I think that will be more useful for us. Okay, cool. So x-axis are the families. I'm only looking at training metrics here. Y-axis is train MSLE, and in color we have different versions. So I started with version 1, the time-based features and linear regression, LR. Then I took a path on what I call, let me add extra features on X. By extra features, I mean, let me one hot encode. I'll talk about this in the end, but there's a whole branch that I followed between version 1 and version 9. There's like 7 or 8 versions that I tried. They didn't work out well for me. This linear regression on very basic time indexes worked the best. Regularized version and yeah, different hyperparameter tuning. You see some families are harder to predict, like school and office and supplies, or wine and groceries. And I zoomed in a little bit just on the very last models that did a little bit better. And I also wanted to look at the challenging categories for all the different models. Believe it or not, this one that's sticking out, myth number 1, that's what I'm gonna ask. Does more training data mean better performance? Like usually when you have machine learning or like deep learning approaches, if you have a longer horizon, you'd expect to perform better. This one that's sticking out that's doing worse is actually me using the entire training set. Or yeah, the entire training set. So it didn't perform well for me. The rest of them used not only the last year, but maybe the last 6 months of the last year of my training set. So clearly picking like your training set is very, very critical and sensitive here. Yeah, then I ignored the one that was sticking out, so you can see how things look like here. The orange one is a little bit better on most categories here than the blue one. Yeah, and for the challenging one, the order is actually reversed, but for the other categories, using like more hyperparameter tuning here, looks like it's doing worse, but let's see in RMSLE what we actually care about. So this is actually submitting this in the Kaggle competition. So the first one gave me a 51, 0.51 score, L2 regularization, L1, LR. Then they were based on, I think, the entire 2017 training data. Then everything else here is based on the last 8 months of 2017, from April forward. That's V9. So V9, and then maybe a little bit of hyperparameter tuning on Ridge. And I tried with different versions of it. The one that gave me the best was this 0.5. Yeah. And if you want to look at maybe one time series at a time, there's 1,800 of them. You can look at time series and the fitted value. Some of them are more predictable, some of them are harder to predict, like this one, for example. Yeah, I keep track of, again, different models, one hot encoding, label encoding. That's the branch that I follow between level version 1 and version 8. I was trying to add some kind of store information or family information in the X training data as features as well. And label encoding didn't work. Again, I wouldn't expect to work with tree based because they would be making decision based on family ID or store ID, which doesn't make much sense. One-hot algorithm hopefully did a better job, but this entire collection or family of algorithms didn't do well for me. And yeah, so
that was expected, right? Because I mean, those are kind of indicator values, right? And they wouldn't necessarily be very good when combined with trends, right? I mean, the linear regressor is not going to do well on this, right?
Yeah. So to clarify, yeah, I had the trend features, the time features, and this encoded family and store ID. So I thought there's some information there that the model can learn, but apparently no.
Well, I think a different kind of model could learn it for sure.
Well, yeah. I just tried linear and XGB. Yeah. Maybe a different one. Yeah, you're right. Maybe more.
That's my intuition. I'm not sure.
That's my intuition too, but to me, they didn't perform well at all.
Yeah.
Because if you look here on my submissions, like the very first one, the linear regression with just seasonality was like 0.51, and then whatever I tried, adding more features, just kept going up and up and up and up. I was like, okay, I'm doing something wrong here. Let's go back to basics. And back to basics means just time-based features, no encoding of store or family ID. Treat them as completely independent time series, and then try different algorithms and hyperparameter tuning, and they did so forth. So yeah, hopefully maybe a better algorithm can give me better results. Right now, I started in 100 and something. And now I am here, 73. So
that's really good. It's really good.
Yeah, and the difference is 0.44, and most of them are about 4.2.
Except for that one guy in first place.
Well, this guy somehow he got very high.
He's made a big jump on us.
Yeah.
So go ahead.
No, I'm going to switch gears to talking about some other solutions, but yeah, tell me.
No, you got to go ahead and talk about the other solutions.
Yeah, I like this guy's Josila's solution here. He used that'll be my next version, but he used all the data. Almost all the high performing models obviously use all the data. I have not used all the data yet. So holidays, oil, and stores and transactions. That was a good one. The other one I just wanted to point out is this hyperparameter here. This very specific time selection is so sensitive that I don't know why. So something is going on, but I haven't investigated and figured out why. But if you change this,
is that what you used? Is that what you used when
that's what I used? That's what I used as well. Yeah.
Wow.
So he does the same. And he noticed that school and supplies is, as we saw in my stack bar, it was sticking out. And then he did something, he plotted it. I don't know, it may be hard here to see, but he used this custom regressor where he says, for everybody, use one model. But if you're school and supplies, maybe use a more complex model like random forest. Yeah, I like that custom one. And then that one seemed to give him way better. But then the question is, why don't you use that for everybody else? Yeah, that's a good one I liked. But again, the question mark is why that specific time period.
What was his score? What was his on the leaderboard?
He was 4.2. He's 38.
4.42. Okay.
Yeah.
A bunch of people at the same level. Yeah.
Right. And the other one, I think we should do another session on just this competition. I apologize for taking so long here, but on the code, if you store by most votes, there's a lot of notebooks that just do basic EDA. And I think to me, that's a good place to start, but some kind of basic EDA, so how many stores are there, how many products, how many states, how many months, looking at sales, what is the highest selling one, clusters. I like this kind of data exploration where you're looking at how the data looks like. Yeah, I just wanted to mention that. Yeah. Cool. I'm gonna stop here.
Oh, wait, one thing, George. So I had a couple observations. I played with this a lot too, and
I saw you climbing, and I was like, David is working hard, so I need to work harder.
yeah, I ran out of time. But if you look at the data tab, go back to the data instead of the leaderboard. Look at the data.
Okay.
And I noticed this. Go open up the oil where it shows the columns and all that, just down below. Yeah, open the one that says oil. Note the dates.
2013.
Now, but look at the spread. What does it go to? So anyway, my point is we're forecasting. You see, we stop, the training data stops at the 15th, and we're forecasting up to the 30th, and they gave us part of the answer. We're not supposed to know this, right?
Hold on.
See what I'm saying?
The 15th, August 15th, 2017 was the last date, right, of the training set?
Yeah, all the other ones that have dates in them, like transactions and all holidays, they only go up to the, see, they stop at the 14th, which they should.
Oh, I see.
Right?
Oh, this is oil data, right? Oh, so you're saying
what's in the oil data? Is it
price?
prices?
It's just the price. Yeah, it's just the price. That
So,
thing on the right.
I mean, the competition occurred after this date anyway, right? So
yeah, but my point is, if you're trying to forecast something in the future, you would have to predict the price of oil on those days, but they give it to you.
right, but since if the competition occurred after the 30th of August, then people could have looked it up anyway. It's like it's publicly available data is what I meant.
I agree they could. My point is, should they? Because it's not really true prediction. It's not really true, right? I mean, I have no problem with it. I was just surprised because they had it in there.
But hold on, you're not trying to predict oil, right? Oil is a feature.
Yes, but you don't know oil in the next 15 days.
Yes. If this is a real scenario, and
you can't do that, right? So
if you're trying
anyway.
to sales tomorrow using the oil today, you wouldn't know the oil today.
Yeah, it wasn't a big deal. I just thought it was interesting that they actually gave you the answer for oil. Because otherwise you would have had to figure out, how do I handle this? Do I take an average price and use that in the future, or what? How would I handle this in my predictions?
Was that the only thing they gave you in advance?
That's the only one I saw. Everything else was cut off at the 14th or 15th.
Or presumably holidays are known in advance, but that is,
and that's okay, right? That's not something. But anyway, it was just interesting. The other thing I tried, George, I actually went and created a hybrid model.
Oh yeah.
I tried to use that thing that you just went over about creating a hybrid model. So I used like a ridge for the linear part. That's the first part of the model, and then I tried like a tree-based one for the next, and I split the features between like the time-based one, the trend-based one for the linear part, and then I use like the holidays and I think like the New Year and things like that and some other things for the decision tree, and it was terrible. It didn't work. I don't know why, but
that's what I'm saying. You know what?
Yeah, I think I need to give the tree-based one better features. So I ran out of time, but I was trying to get some of that store information in there and things like that might help it.
Okay, this is the conversation is getting super interesting, and we can get lost here. So I think we should pause here and do a third time series just on this competition sometime in December, January. Because I have a whole here section of notes, and anything that makes sense to me, like, didn't make sense to me here. Like, more data means better performance, none here. More complex models makes better performance, heck no. Like, more features, better performance, no. Like, it was testing all my hypotheses, and it was like, it was giving me this signals that something else is going here, and I don't know why, and I need to figure it out.
It could be on a longer term. When you have more data, there's additional things that are coming into play that we don't have any way to get a trend of or seasonality. They're very random. So maybe
there's a trade-off between looking further back into the past for data. There's a trade-off between increasing the amount of data, which is usually a good thing, and distributional shifts, which could be part of the reason that the shorter time frame models are working better here.
Right.
Yeah.
But yeah,
I think there was also a data quality issue in this data set as well,
Big
right?
one, huh?
Especially in the early years.
Mm-hmm.
Oh yeah. In some of my notebooks, yeah, you'll see those missing values. Yeah. And again, the three of us got together and we talked, before this session, so we have way more a little bit higher intuition. But yeah, this is a very interesting challenge, and I can't wait to revisit it because it's been a week now. I've been relentlessly trying it and getting better. Whereas the things that I think would make sense are not making sense, and I love to hear what others think as well. Okay, gonna switch gears here, open it for questions, and we have 3 more things to talk about in no specific order, but I'm gonna exit the floor, so give the chance somebody else to talk.
No questions?
I was kind of thinking, like, have you considered like doing PCA sort of thing on the features, and then like I'm just thinking about the method that the other guy used by using different models based on clusters that PCA will give you. Maybe kind of like building a custom ensemble method for dealing with different sets of data that might behave in a different way. So that you might end up with like 3-4 vectors, and you can just maybe cluster those together. Just an idea. Predict using the PC. So each you can make predictions based on each vector, and you can treat each vector as a time series that way.
I haven't seen that. That's interesting. Yeah, if there's any notebook out there or resource.
I have been working on something similar to this.
Slack. Yeah, that'd be
yeah. I'll be sharing with you soon.
I'll share our Slack as well in case people want to join.
I think another thing that we could stand to leverage more in the models that we've tried so far is the cross learning from one store to another, from one type to another. There's the linear models, for instance, are really fitting each series as if they're independent.
Right.
But there should be some relationship between beverage sales in one store and beverage sales in another store.
Yeah.
Or one store's beverages versus that store's food or something. Right. By fitting each of these independently, I think we're not taking advantage of the interactions between the quantities we're looking at.
Right. Yeah, that was me trying to throw more features at it to encode those interactions, but they didn't.
Problem with more features might be that you might be adding too much noise if they're correlated. And that's
well, I mean, yeah, just an indicator that this is ID store 1 and family 1. Like somehow you need to identify that this is the time series.
But I like the idea of doing some kind of unsupervised learning to cluster even. You could cluster the different types of categories and stores together and then maybe benefit from more data on each of them. So
there is the stores.csv that has that clustering of stores. I'm hoping that will give us some better intuition instead of just label or one-hot encoding them. Yeah.
Maybe, but we don't know what the basis of their idea of a cluster is, right?
Yeah, maybe geographical or yeah. Oh yeah, I don't know how they came up with that cluster idea. I don't know.
Right.
Cool. Thanks for sharing the link, Arash.
So I can talk about another model.
All right, go for it.
We're ready. So I'll share my screen. Okay. You guys see Rocket?
Yes, ready to launch.
Okay. And very cleverly, I put mini Rocket smaller. So Rocket is an approach to time series that, at least right now, is pretty much considered state of the art. Actually, Mini Rocket is. It's very, very fast compared to other state of the art time series models. And when I say fast, in the papers, they talk about some of those results with Mini Rocket, where the next closest in terms of accuracy and state of the art is on the particular data sets they were looking at was taking 19 something days to train on a given platform, single CPU. And Mini Rocket takes 8 minutes with better accuracy. So it's a substantial difference, huge difference. And so I'm going to go ahead and, oops, I get to go to the next screen. Okay. So Rocket was, I've got the link here to the paper. I've read through the paper. Rocket stands for Random Convolutional Kernel Transform. It's specifically aimed toward classification. The paper talks about classification with time series, but you can apply it with regression as well. Works perfectly well with regression, and there's actually regressors, Rocket regressors out there. I'm not going to go through great detail because we don't have a lot of time here, but the method involves taking 10,000 random kernels, just like you would in a image model where we do convolutional layers. And they're applied to the time series to produce output features, right? The difference here is these kernels, when you do like an image or even time series with CNNs, you're very specifically defining things such as the length of the kernel. The kernel is like the filter, right? So the dilation, the padding. If you've looked at our earlier courses where we went through this, we talked about what these, padding and kernel filters and all that is. We also, when we do that, we let the model learn the weights and the biases that go with those kernels. Here, we're just using random values. Now, when I say random for all this, there is a range that they choose to use, that they did quite a bit of different studies to try to figure out what was the best range of values. But within that range, it can be a random number. And they use 10,000 of these. That's also tunable, but they found that 10,000 works very well for what they were doing. And then at the end of this, they do a type of pooling. If you recall from a lot of the image vision work that we did different types of pooling. They use one called proportion of positive values. They go through this in the paper, but this is known as PPV. And they'll apply that to the output of all those kernels. And from that, they get a gigantic set of features. But these features are then fed into a linear model. And the linear model actually produces, a linear regression model or a linear classification model produces the result, so the prediction. And so it's kind of a novel idea. The idea is you're basically transforming all of your input time series data and then feeding that into a linear model. So surprisingly, the novelty here is all this work they do to transform the features ahead of time. And so it's an interesting idea with great results. It's very, very fast.
Can I ask a question?
Yeah, go ahead, ask a question.
These kernels, they're random, they're not learned, right? They're just
nothing is learned, everything. So they set limits on what the range of weights can be, and they just randomly pick in that within that range. The same for the bias, the same for dilation, the same for length and padding. Dilation is really interesting here because most of the time that's not something you play with a lot. But here that's a very important step for this, is to let that dilation have a range and then use random values in that.
So the actual learning and fitting only happens at the very last linear model?
In the linear, yeah. And they have a lot of background on why this idea that producing these kind of features captures, as the way they say it, you're randomly capturing some of the features, right, that are actually there. Whereas when you're having to learn it, you're trying to learn like specific features, like edge detectors in an image or something. Here they're saying this is enough. That doing 10,000 in these enough captures partial features basically, and then the linear model can take that and learn the rest, right? So it's a very interesting concept in my opinion.
Right. Yeah, I agree.
Yeah.
David, this is a time series, so this is a 1D kernel, I presume. It's just a 1D convolution as opposed to like the images, which are like a 2D.
Yeah, that's right. So a few years later, this was from a group, Monash, I believe it's Monash or Monash University in Australia, that put this out. They improved their model or their method and produced another method called Mini Rocket, which happens to be up to 75 times faster than Rocket, and with slightly better accuracy even. So here's the link to that if you want to read the paper. The difference in this one is that with this one, they used 10,000 non-random kernels. So here what they did is they decided that this idea of producing random kernels with all those different combinations of the length and the dilation, and the padding and the weights, they decided to fix these to certain values, and they did a big analysis to see which choices were the best. So again, we're not learning these in a sense. They've just kind of done a study of what works best for a whole bunch of different time series, and they said, okay, we're just going to use the non-random ones. Again, with the hope that on every time series it encounters, ones it hasn't seen before, it'll still be able to pick out partial features that'll be useful for the linear model to actually learn the regression with, right? They also introduced 4 key ways of optimizing this transform. Part of the fact that it was no longer non-random allowed them to come up with these optimizations they used. So that actually sped up the transformation part. And then there's nothing new as far as the linear part. It's the same as they use for Rocket. They'll just apply a linear model to it. So this is Mini Rocket. Next thing I wanted to, any questions on Mini Rocket? Again, the paper is very detailed. I don't have time to necessarily go through the whole thing.
Right. So that fixing and not generating random kernels and this optimization make it 75 times faster, I guess.
Yeah. Yep.
Cool.
And it just happens to be slightly better accuracy, maybe because they specifically studied what non-random kernels would be the best. They didn't give a lot of detail for why it might be a little bit more accurate.
Right.
I'm going to share. I tried to use this actually. So here is Mini Rocket. Is that too small, or do I need to increase it a little bit? Maybe I'll increase it a little bit. Is that better?
Right, perfect.
Okay. So I have wanted to apply Mini Rocket to the same competition that George was going through. So I actually did this over in Collab. I had some trouble trying to install things on Kaggle. I think it would work now because I figured out that this is all I need. But for Collab, I had to install stats models to get a newer version than they had. Also SK Time. So SK Time is a really nice time series library, and it takes a lot of input and things, and the way it works is modeled after sklearn. So it's very intuitive if you used sklearn a lot to use SK Time. At first, I didn't think they supported Rocket, but I found out after doing some more research that they support Rocket and Mini Rocket. So I'm going to import from SK Time this transformations Rocket, Mini Rocket. I'm going to go out to Kaggle and retrieve all the data that we've seen before, all the stores and tests, CV, transaction, holidays, and of course the training set. I'm going to pull in the holidays, the training set, and do the same kind of prep of the data that George showed. We're going to change the index to have the store number, family, and date. Here's a little sample of some of that training data. all we have here is the sales. I didn't actually use the stores. That was my next step, was to bring in some of that store data. But so the first thing we're going to do is generate some features and labels. I don't actually use this make flags routine, but here it was. I was working on doing some of that. I haven't got that to really work well yet. Primarily because of what I talked about for predicting the lags for the future when you're doing the prediction that you're going to submit. I haven't worked out how to do that yet. George showed you how you can unstack the training data to get your Y values. Here they are for every family. And then here's the holidays. Here I'm producing the trend data and the seasonality. So you get that. Here's just a look at those columns. And here's a look at those values for each state. So that's going to be our standard trend and seasonality features that we're going to feed in. One thing that SK time, this is where I spent most of the work here, the effort, was to figure out how to convert this into the type of input format that SK time wants time series to be in. It's very specific. Luckily, they have some helpers for converting from different types of data into what they want is kind of a nested data frame. I'll try to show that a little bit. So I'm going to import those, and right now, we've got this array looking like this, but they want to produce, and you consider these are all those, constant, trend, and seasonality, as you go down, right? So instead of that, they want it to be in these, what they call dimension columns, and all of that data is nested inside of that column value. So you can go through some of their converters to get this. So here I'm going from a 2D array to nested and using that converter function they have. But it took me a while to understand this and how it's working. It's not easy, but that's what you need to do for any of the SK time.
So sorry,
library.
The data is in the column itself. Is that what you said? Yeah.
And in our case, we have a very simple thing with one dimension, but you could have a time series that has a bunch of these. They go through it in SK time documentation while they do it, but it's kind of hard to follow the first time.
And each record is a different record from a training set, right?
Yeah, this still applies like to the dates up here, right? So,
right.
Once you get it transformed into the input that it expects, you can then transform the features with Mini Rocket. Remember, that's what really it does, is it transforms these. So instantiate Mini Rocket. You're going to fit these values, this SK time input, and we're call transform on it. It's very much like an SK time, or a SK learn encoder in a way, the way they're, you fit and transform and all that. So here's the output, this nested transform. And so we went from, I don't know if I printed the shape for this one. So we go to this weird 592 times 996, right? So we originally had, I used year 2016 and 2017 as training. So I had 592 days worth of training data, right? Mm-hmm. And I had these 16 trend and seasonality features. So it changes that when we do this transform into the 592 days, but now we have almost 1,000 or almost 10,000 features coming out of this.
Probably by each kernel, we have like 10,000.
Basically, yeah. Basically, almost 1 per. And then we're just going to fit it with a simple regressive model. I'm using RigCV, nothing too special here. Call fit on that with our Y values that we had before. And then I wanted to test with the competition metric that George mentioned, this root mean squared log error. So I have a function that will allow me to calculate that. I made the predictions on the test set, this X nested transform. And one thing that this function doesn't handle is negative values for predictions. So if the prediction was less than 0, I just set it to 0. Mm-hmm. Apparently you get some negatives occasionally and that'll throw it off. So I just set it to 0. And when I calculate that, it's 0.63. So not great. Actually, I did at one point put the lags in there and that helped a lot. It got down to 0.476. But like I said, I hadn't worked out how to do this for the actual test data. So that's my next goal is to figure out how to do it. For
so these numbers are on the training set, right, David?
This is on the training set. Yep.
Perfect.
That's right. And then of course we want to predict the next 15 days. So you do the same thing to produce your test features. And again, we've got to convert it to SK time, a nested data frame basically. And we're going to transform it with that same mini rocket model. This time we're just going to call transform. We're not calling fit. We use the fit on the training data, but here we do the transform and we get our nested transformed features. And we can call our model and predict the values on that. Again, I just removed the negatives and I produced this and submitted it. Let me get down here. I call the Kaggle function to submit it. And I was going to show you the results. Sorry, should have shared my screen. So here, let me share my whole desktop. Okay. I think I have. Oh, sorry, I did have it here. Okay. Pull this down. So this, I believe, here is that actual submission. So this is Mini Rocket trained with 2016 through 2017 data, and I guess I need to take George's approach and do April through 2017 of August. But that was actually, of all the ones I've done so far, that was the best. This Mini Rocket was the best result.
So all of them are Mini Rocket based. Let me see, Mini Rocket.
No. My original ones were some of the just straight, different linear models and such.
Right.
Um,
and then Mini Rocket with different features like holidays we see or
yeah,
time ranges.
Yeah, right. So I actually, that didn't help.
But this is more stable. Like for me, if I do all the data, like all years, it's not 5, it's like way higher. And same with 26.
Right. It seems to be fairly
pretty stable
good at handling that, surprisingly. But again, the best was, and maybe the next step for me is to try that smaller, very much smaller theory that you trained on.
That worked for me. I don't think it's gonna work for Rocket. Yeah, let's see. I'm curious.
You never know. I mean, there's maybe something specific about that it's very
right.
That training data, that period may be very similar to those 15 days we're trying to predict. So just as Robert said, the distribution might be a really good match, and that's just by chance, really.
Yeah. I'm wondering if Rocket, based on the way you've described it, is a little bit more robust to distributional shift because it's got that kernel.
Could be. Yeah, especially the fact that when I trained the larger all years and 2015, I didn't get a huge change. So.
Yeah, I find it weird that 2017 is such a high RMSLE. I wouldn't expect that.
Yeah. Yeah, it didn't do very well there.
And the hybrid one is, you said, linear and tree-based?
Yeah.
Cool.
And I think I just haven't got good features in for the tree-based part yet. That's my suspicion.
Right. Cool. Yeah. When we revisit this competition, when we add all the features,
yeah.
Let's see what Mini Rocket and other approaches do. Nice.
All right.
Cool. Thank you, David. I'm glad you tried it in Colab as well. That was a nice touch. Okay, we have 2 more things we want to talk about. Should I go or should you go, Robert?
I don't actually know what are you doing store sales as well?
I only need 5 minutes, so I can go next if you don't mind.
No, I should go next then because it's again store sales.
Oh, okay, go for it.
Again, it's it's almost 8:30, so we don't want to take too much time on this, but we did think we would be remiss if we didn't talk about a very famous competition in this space, and that would be the M5 competition. So let me introduce that. This is many of you may be familiar with this estimating the unit sales of Walmart retail goods competition that was conducted during 2020. It's actually the latest in a series of historical competitions that go way back to the early 1980s. And that's why it's called M5, is that it has evolved over the years, and when an evolution is significant enough, I guess it gets a number change. So there's been I guess there were M competitions were introduced in the early 80s by faculty at University of Nicosia, I think, on Cyprus. This Spiros Makrodakis is emeritus professor there, and he has been involved with, I think, all of them over the years. This particular competition, there's a link here with a whole lot of information on it, so maybe what I should do is just share some of these links in case folks want to look them up. We're not going to be able to go through too many of the details here. So to a very, very high level overview of it, we are trying to predict individual product sales through Walmart. We're looking at 3 states, California, Texas, and Wisconsin. I think it's just a subset of the stores in those states. We have, let's see, so 3,049 different products that we're trying to do a regression problem on these time series. 3 categories: hobbies, food, and household, and 7 different store departments that we're looking at. The data set is here. It is some information about the calendar, which is the same time-based features that we've seen in the other notebooks. We have a training data on sales. The validation, I believe these are basically the same, just the one has a few more dates. And pricing. And the idea here is that we have roughly 5.5 years, something like that, 1,900 days worth of data in the training set. And we are being asked to make 28-day forecasts. So at any given day, we are supposed to forecast what the number of sales over the next 28 days is. So what they provided is this train set, and going up to 1913, but then also going up to 1941 will be the labels used for the public leaderboard. And then beyond that, there is a private leaderboard of another 28 days. So you get everything, including labels, for the first 1,900 and some. You get the next 28 days. You have some features, but you don't get the outputs. And then the 28 days after that, you are completely blind. Let's see. So there were a few interesting things. Actually, you know, the best resource for this to learn about this competition is one of the ones that's linked on our meetup page here. It's this ResearchGate publication, Results, Findings, and Conclusions, and I've got it open here. And this is written by Spiros Makrodakis and 2 colleagues in Cyprus, or I guess the other 2 are in Greece. And they describe the competition, the history of the competition, some of the backgrounds, the rules of the competition. This was a little bit interesting here. There's a chart which starts to illustrate the way that this competition was scored. The scoring is a little bit interesting. There were 40-some thousand different things that you're being scored on, but you're only submitting the predictions for 30,000 quantities. And the reason for that is that the other 12,000 are aggregations of the original 30,000. So you only submit 30,000, but you're being scored on those plus aggregations derived from them. So there are 12 different levels in which you're scored on. The lowest level here is the only one that you actually submit for the competition. The unit sales of product I aggregated at a store, and then every one of these other things can be derived just from combining these information, this data down here. And overall, there end up being 42,000 series that you need to predict. And the evaluation metric here is given by, is it up higher? I think it's down. Yeah, performance measure here. Root mean squared scale error. And the reason that we're looking at a complicated looking metric like this is that the units of the different products are very different. We saw this in the Ecuador data as well, right? Where we might have the hardware family of items only had 5 items sold, while the beverages family had items in the tens of thousands. So if you want to fairly score a model that can do well on all of them, you do some sort of scaling to take that into account. So this scaling is done using the squared variation, or the squared differences of the values from one day to the next. And then when you have the RMSSE, there's a separate weighting factor that goes on the front of that, which I didn't see much information about these W's in this document, so I'm not really sure what exactly was going on here. It did imply that it was assessing some kind of relative value of predicting each of these series. So that was what they wanted to optimize. If we come back to the Kaggle chart here, we get a look at the leaderboards, and you can see that the, well, if we start with the public leaderboard, we've got a lot of people who did phenomenally well with errors of 0.
What?
And turns out that the private leaderboard has a completely different cast of characters. Who would have thought? So the #1 place actually jumped up 1,500. I think he was ranked 1519 in the public leaderboard. So the scores here on that particular metric are 0.5, a little bit above 0.5. 0.52 was the winner. And so what did each of these competitors do?
You know why there was such a big change? Was it people gaming the system somehow?
Yeah, I mean, it looks like people were just
probing the test set.
Probing, yeah, exactly. It looks like enough of them to fill up the whole page. Anyway, I guess that's what happens when there's $50,000 of prizes. I don't know. So, a couple of things that we should note about this competition as compared to past the M4 and previous competitions. This one was deemed to be a more relevant challenge for a variety of reasons, and this paper here went into that, and I didn't pause over the text there because it's gonna be difficult to follow over a Zoom. But the outline of it is it was the first one of all these M competitions that was held on Kaggle. So the thought was that you would draw a much wider audience on Kaggle and might have a stronger competition. It also was the first one that had not just time series to predict, but also, or not just time series provided, but a lot of other exogenous explanatory variables, events, holidays, other explaining factors that could affect people's predictions. And so it would be interesting to see how people would use that data. Another really important aspect that many of the competitors leveraged is that this data, as you can see, and as we noted during the Ecuador sales data, there's a lot of potential to leverage the cross correlation between the different series. So you might have one product family might do similarly in Wisconsin as it does to Texas because there's some national phenomenon that's changing sales patterns, maybe a cultural phenomenon, maybe related to holidays. These are all things that just having more data across stores can help you to learn. And models that are able to exploit that can do quite well. My understanding is that past versions of the competition may have had a bunch of independent series that didn't have obvious relationships between each other. Another challenge introduced in this one was intermittency of data. I guess there were a lot of zeros in the data set, just places where the data were missing, and that was a new challenge as well. So let's quickly go over to the winners of this competition. The leaderboard here, the first place contestant actually is he was an undergraduate student from South Korea, working by himself.
Right.
And that got a fair amount of press because it's not often that.
Yeah. Do you mind opening a link I just shared, Robert? There's a recap of the competition, and like his approach was very simple. Yeah, if you scroll down, so there's 7,000 participants. Then scroll down, the first comment. Go a bit more.
First comment. Oh, there we go.
Yeah, this one. So yeah, there's a picture of Mr. Kyung, and yeah, it says undergrad computer science at South Korean University. His LGBM method was the most accurate than all other submissions, and he just did this with the Kaggle notebook. You know.
Yeah, so what was particularly noteworthy about his version, and I really didn't step into the details much, just read the high-level summary, is that he took the light GBM model and basically did some, tried a bunch of different time series windowing. I think he tried six different time windows, and then did some probing to look at how the mean and standard deviations of his predictions were varying across the different choices he was making, and then did some kind of ensemble method across 220 different LGBM models that he had, or no, I think he selected a small number of the models based on his mean and standard deviation assessments. Wow. So kind of a combination of a simple method, LGBM, light GBM, plus a rather novel approach to fine-tuning the data, if you will.
Is that shared anywhere, or is that just at the high level discussed in the?
So there was this discussion here.
Okay, he himself talks a little bit about it, I guess.
But there's no, I don't believe there's a notebook. Oh wait, there's this, yeah,
It
the
doesn't work.
summary. Not found.
You said it's an assembling model. Is that what it was?
It was an ensemble of a small number of light GBM models.
And the novelty was in the data preparation part?
And also his use of the Tweedy function as an objective. A lot of the top performers in this competition used that. The Tweedy distribution, the only place I've encountered it previously is looking at distribution of insurance payouts. So if you have a certain number of customers that you're insuring, and the vast majority of them make no claims, but those that do make claims could have a wide variety of expenses, the Tweedy distribution is the mathematical result that falls out from that.
Yeah, there's some in sklearn. There's some Tweedy regressors.
Yeah, and I think in the other window here I had something open about one of those.
Yeah, I think, but like you said, I think they're
This
very
one.
good at handling outliers or something,
Yeah.
something like that.
I missed this. How does this distribution come? Is it from a natural phenomenon, like, or?
I don't remember what the assumption is upon the claims themselves.
I mean, where does this distribution show up? Like Poisson is like in arrivals, right? But where does this one come up?
So Poisson would be arrivals if you're just dealing with counts.
Okay.
Tweedy is kind of another layer on top of Poisson, where each event has a value that can vary.
Okay. Like a multi-output Poisson. Not multi-output, but a value Poisson. Okay.
Yeah, and I don't know if it's a family of models. I haven't used it. I've just read about it here and there.
Okay.
Yeah, the notebook. I'll link to that.
Thank you.
So the second place winner, let's see what got his up here somewhere. I think he put his notebook was accessible from the leaderboard. He also used light GBM and tweaked it by using a model that was created actually with the deep neural nets called NBeats. And it's presented over here. So a good amount of
feature engineering plus deep learning, is that what it was?
Yeah, light GBM plus deep learning.
Oh, like some kind of ensemble of both?
Now the third place one used only deep neural nets. But most of the top performers were using light GBM. And if you look at that paper, let me put, oh, that link's already in the meetup page, so that's fine. The paper here, they have some interesting conclusions about the techniques, and the very first observation that they make is finding one down here. The superiority of simple methods.
Right. That's the beauty and challenge of time series, I think.
Some other things that they mention are the value of ensembling. which is the second finding. The value of this cross-learning, being able to learn something from a similar quantity being calculated somewhere else. Finding 4 was that the winning methods were actually doing 20% better in terms of the weighted RMSSE than the benchmarks that had been published beforehand. And the reason that that number was significant was it suggested that there's a lot of room for the retailers to forecast their own data better.
But this weight, we don't know exactly how they're calculated, right?
That's correct.
Okay.
Or we might, but I didn't see it.
Mm-hmm. Maybe some kind of business metric out of sales. Maybe some items are more important than others.
That's the impression I got from reading the part here that was describing it.
Okay.
The external adjustments, such as the mean and standard deviation method, or the second place person's NBEATS method. Cross-validation strategies, and some of the explanatory extra variables.
So cross-validation strategies makes me think that the data sets weren't as big. I thought this was like very large data. Is that not right?
1,900 days times about, what was it, 30,000 or 3,000 products, 10 stores.
Let me do some math.
Yeah. I always think cross-validation is really important when you have a smaller data set and you don't have a nice similar distribution in your training, your validation data and all that. But maybe here that's the
I think
case.
the term cross-validation may be not what they mean right here.
Okay.
Yeah.
The cross part of it.
Got it.
You have to respect time dependency, right? You cannot just pick random.
And validation strategies, right? Cross-validation is difficult to do with time series for the reasons you just mentioned. The causality.
Causality needs to be respected, yeah. But in 1,900 days is what, 5 years of data across 3,000 times 10, 30,000 different time series, I guess. Okay. Well, the scale is insane. I mean, 5 years is not much, but the scale of stores and products.
So the only other thing that I wanted to mention is that apparently there will be the next version next year in 2022. So
let's get ready for it.
M6,
there we go.
or is it just M?
DLA submission, guys. We got the.
It wasn't clear. It might still be the next M5.
Could be. Yeah.
Let's practice on the previous M's. Let's practice on the Ecuadorian first, trying to figure out what is going on. Cool. Thank you, Robert. That was very, very useful. I'm glad I put the summary findings together, that give you the information you need without going through all the notebooks. Cool. David, did you try anything else while we were talking, or?
So yeah, I did. I ran MiniRocket on that shorter time frame that was optimal for a lot of people from like April through to the end.
Yeah. And
it did phenomenal on the training set. I got an RMS, whatever the logarithmic one. A 0.26 would be, which would be at the top of the leaderboard if it transferred. But when I submitted the test predictions to Kaggle, it got like 0.65, so it actually got worse. So I was speculating with George that it may be overfitting, the linear part is overfitting the data. It's a much smaller data set, and it just doesn't apply as well when it tries to fit. I'm not sure, but
yeah, what I observed from my experience yet was opposite for mini rock. Like your was very stable. For me, if I deviated from that, like the best one was that April forward. If I went 2017, I reduced a little bit in performance. If I went 2016, 17, I reduced more. And if I went even more, I reduced even more. But for you, there wasn't such a linear or such a highly correlated performance.
Yeah, as Robert speculated, it may be a lot more robust to that type of distribution change shift.
Oh, let's keep looking at it. Yeah, maybe next month, next couple of months, we can revisit this. I'm very interested in this. It's like one of those things that makes you wonder what's going on. Cool. 6 minutes. I think we can make this happen. The only last thing I want to talk about was Prophet, which is this library, Python and R library from Facebook/Meta open source. I didn't get the chance to use it for the sales competition, but I just wanted to share with us a little bit of how does it look like, how do you install it. So in Python, you need this PyStan module, which is a library for Bayesian inference that is a requirement for Prophet, and then you just pip install Prophet. And then how do you actually use it? There's a quick start tutorial here. It expects, believe it or not, your X's to be, so yeah, import pandas, import Prophet, from Prophet, import Prophet. The X's should be just two columns. One should be a timestamp, any format, doesn't matter, and you should have your values. So clearly, this is not going to work for our source sales, but hold on to that. We'll get to that later. And then, yeah, you create a new Prophet object and you feed your data frame. And the goal is you learn from this is a single time series. You learn some kind of model and you're able to predict in the future. Then how do you make predictions in the future? You create as many periods as you want in the future. In this case, we're creating 365 days, just the x-axis or the time axis. And we call predict method on this x-axis, on this y-axis. And Prophet actually gives you a lot of results. In this case, we're interested in the time index, the actual prediction, and the lower and upper bound for that prediction. It has way more outputs and results. I didn't get the chance to go through all of them, but this is how it looks like. It also has like a nice plot capability. So you can look at your x-axis DS and then your y values in black. And in blue is the actual forecast, the trained or fitted values, and over here is the forecasted one for the 1 year. So the other thing is that internally you can investigate the different components and make up the model. So it has the trend component, like we've seen in our time series journey. It has a weekly seasonality component and a yearly seasonality component. I don't know if you can change this or if you can add or remove, but it looks like these are the very basic 3 components in the model that it builds internally. It has some more interactive plots capabilities as well. The other thing I wanted to touch was you can add holidays and special events. So let's say you have something like this, and you know those are special. Oh, sorry, I'm looking at our. If you know these are your holidays, you can easily include them as holidays. That will give you better performance. And the other thing I quickly wanted to mention was this additional regressors. So if you saw the very basic model only has an index column and a target column. What you can do though is you can add what is called this regressor. And that means that any other feature you want your data set to have, in this case would be our store ID, family ID, whatever you want to add, you'd call this add regressor. And that would be your extra feature for your X, so that X is not a single column.
But should those be time-based columns, like, something that's,
they should also be time, not time. So one row is, so each record is, right? So yeah, I don't just have the time index and the sales, but I might have something else for each day.
but it's got to be something that's kind of date related, right?
Right. So in this
Store
case, if it was
wouldn't
store
be
ID,
date related, right?
if it was store ID, this would be the same. If it was
Well, I
family
don't think store ID would be date related, right? I mean, it doesn't seem to be
it's
something
not,
that would,
it's not. Yeah.
but you could try it in there and see, but I don't know.
Right.
It could be. I mean, it could learn. Well,
In our case, we had promotion. How many items were on sale? So that is days
Right.
dependent. But if somehow I want to encode that this is this store ID and this family item ID, it would be just the same value. That is that. Yep, the rocket that you mentioned, M5 that you mentioned, and then NBeats, this package that was it second or third? There's also an implementation of it here. We haven't gotten the chance to look at it yet, but there's a paper behind it. Maybe we can look at it at some point. The regressors. This is another notebook that's trying to predict weather-related metrics. So yeah, if you had like temperature, rain, maybe something related to the sun or wind, you would add it to your Y. But yeah, you're right. They're all date related. Cool. That's all we had, friends. This was an awesome session. Yeah, I definitely want to come back to this competition and see if we get any more insight on how to improve our leaderboard skills here. All right, I'm gonna quickly just mention what is coming up, and that's it for tonight. So that concludes our two-part series on time series. In 2 weeks, we're gonna take a break for Thanksgiving. We're gonna talk about this bonus content that Dimitri is gonna lead on transformer and attention-based models on another competition. So if you get the chance to check it out, please go do so. Then in this, and we're going to switch gears. We're going to talk a little bit about this AWS Cloud Practitioner certification. And again, the goal is to prepare us for the machine learning certification. That's what we care about. But just to get some basic familiarity with AWS services in case you're not, that's we're using this as a stepping stone towards this machine learning. We want to do this for AWS, Google Cloud, and I think Arash just volunteered to do for Azure sometime in February, March, whenever we release this there. That will be 3 clouds. Look at that, multi-cloud. I don't know if anybody else uses, what is the other one? Baidu? No. IBM. I don't know, there's a few others out there.
yeah.
I just care about the machine learning part of it, honestly. But it would be nice if we can have like an overview of the basic services and okay, how are their services look like.
Might be beneficial to do a quick one, George, also on Databricks.
Databricks, okay. Yeah.
That's coming up quite a lot nowadays because of large data sets.
So I've heard Databricks, I heard Snowflake, I've heard Data Robot, I've heard all kind of data-related services and companies.
Interesting enough, 2 days ago, I think they raised another $1.6 billion. Evaluation for Databricks is now 38 billion, I think.
Oh, wow.
It's quite I think it's like 4th or 5th biggest, I think, kind of like startup companies in the US right now.
Cool.
Probably exceeded SpaceX, probably. I have to check. It's crazy.
Until SpaceX lands on Mars and things will change. Cool. Friends, this will be posted tonight or tomorrow here. You'll see it I'll actually upload it on this Kaggle courses mini series. So yeah, if you like this, there's a whole section here that we've covered. The part 1 is there as well, and part 2 will come hopefully tomorrow. Well, that's it. I want to thank everyone for sticking with us, and thank you, Robert, and thank you, David, and thanks everyone for participating. Very interesting challenge, very interesting session. We learned a lot, and hopefully we can go to sleep with a sane mind, because I was going crazy. Anything that made sense in deep learning made the opposite sense in this time series competition, which is interesting, you know. You should have a collection of tools, not just one tool in your tool set. Cool. Thanks everyone, and for everybody watching on YouTube, thanks again. Feel free to comment, like, and subscribe, and yeah, we'll see you a couple of weeks. I'll stop the recording here.